All right, switching gears a little bit, moving from the distribution of sample means into the distribution of sample proportions. And let's first of all, let's think about why it's reasonable to study sample proportions. First of all, not all data is quantitative. Quantitative data like ACTs and IQs and things like that turn out to be nice numbers, nice quantitative variables. Uh, but again, that's not always the case. A lot of times we get into categorical data, and our categorical data are typically reported as percentages or proportions. Now, a variable that I think is quite interesting because I love to travel, and where I want to travel to usually requires flying. So I don't like flying. I wouldn't say I have a fear of flying, but I just don't like the hassle of the airports and the hurry up and wait kind of mentality. But some people have a real fear of flying. In fact, I just looked it up. There was a report recently that was reported uh, said, uh, well, again, let me explain the variable. The variable of fear of flying is categorical because you're either afraid of flying or you're not. So obvious categorical data. Reports, one that I ran into recently was that 40% report some fear of flying, and actually 3% report their fear of flying to be at a level that would classify as clinical phobia. Now, again, these statements right here are for the population, right? This is explaining everyone, all people, how many people report a fear of flying. Now let's switch gears so I can motivate the idea of well, I can motivate the notation. Let's say that we take a sample of 1,500 people and 630 report some fear of flying. Now the notation, the point 40 would be represented by my p. So p is the population proportion. It's the percentage that explains everyone. The sample that I've taken is only 1,500 people, and 630 of those have responded that have some level of fear of flying. So if I take 630 divided by 1,500, I get 42%. Sample proportions are typically reported as a decimal, so I would report this as 0.42. Now, a little bit more about that. A sample proportion which is described as, for the notation, is p hat. It's p with the predicted thing above it, but we're really not predicting anything. It's just a different context than what we saw with the y hat back in regression. But p hat is found by just taking x over n, where x is the number of people from our sample that have the particular characteristic that we're measuring, in this case, fear of flying, and n is the total sample size. So for this illustration, x is 630 because there were 630 people in this fictional example who report a fear of flying, and 1,500 were sampled. So again, my p hat is 0.42. Now, switching gears to the central limit theorem, you're going to see a lot of similarities from the central limit theorem for sample means to the central limit theorem for sample proportions. Speaking of, let's see how this just plays out. Let me see if I can. Uh, yeah. So remember when we went through the central limit theorem for sample means, what did we do? We started out with a population where the mu and standard deviation were known. Well, we're not doing sample means now. We're doing sample. Well, I'm sorry, we're not doing means now. We're doing proportions. So P is what is known. So if you want to bounce this off some example, like the flying example, P would be 0.40 because 40% of everyone, our population, fear of flying. The next thing we do is the sample size to be a normal distribution. You remember that if it's normally distributed 2 or larger, not normally distributed 30, 25 or 30 or larger, doesn't apply. But what does apply is we need to meet this criteria, that n times p has to be greater than or equal to 5, and n times 1 minus p must be greater than or equal to 5. If that is true, then we can go ahead and use this information. If it's not true, we got to pump the brakes. We don't have a large enough sample size for all this stuff to be true, all right? And I'll illustrate that in an example here in just a second. So we're going to set n to be 1500, just because that's a number that I selected earlier for the sample size. We dive into our population and pull out 1500 people at random. We ask them, do you have a fear of flying? We get a p-hat for the first 1500 people. Let's just say, for the sake of just having some numbers in front of us, that 592 out of the first 1500 reported a fear of flying. That would be our first p-hat. We throw the 1500 people back in the mix because we're doing this with what's called with replacement. We pull out 1500 people at random. We ask them how many have a fear of flying. Let's say that 613 of those 1500. Again, we don't know these values and we don't need them. I'm just presenting these as an example because I want you to know that p-hat1, p-hat2, and p-hat3, first of all, will vary. And I want you to know that these are nothing more than proportions. I can put 613 divided by 1500 in my calculator and get a point, well, let's just do it. 613 divided by 1500 is 0.4087, a sample proportion, right? So anyway, I can do this for the first sample, the second sample, the third sample. I can do this forever. And what will I get? Well, previously I called these the distribution of sample means, didn't I? But it should make sense now that I call these the distribution of sample proportions because we're dealing with categorical variables and proportions, or the way we measure that. Central limit theorem tells us the following stuff. As long as n times p is greater than or equal to 5, and as long as n times 1 minus p is greater than or equal to 5, these values right here will be normally distributed. Why is that cool? Why is that needed? So we can use that key. Otherwise, we don't know what key to use, right? We need validation that our distribution is normally distributed. If we have a normal distribution, remember a normal distribution is defined by its mean and its standard deviation. So if we know these things are normally distributed, first question is, well, what's the mean? Well, the mean just turns out to be the p that we started with right back here, 0.40 in the flying example. The standard error is, again, the standard deviation, population standard deviation notation with the sub p-hat, because we're dealing with p-hats over here, is p, in our problem, 0.40 times 1 minus p. Well, 1 minus 0.40 is 0.60. So 0.40 times 0.60 divided by n, which in our illustration was 1500, right? Now, don't get sloppy, and I see this all the time. I see students they actually know what they're doing, but they get sloppy. I can't tell you the number of times that I have seen something like this happen. I can't tell you the number of points I've taken off. People know what they're doing, but they get sloppy and they don't put everything under the square root. So don't do that. I mean, if you want to get the problem wrong, then do that. But if you want to get it right, that's not going to work. So make sure the p times the 1 minus p divided by the square root of n, this is all under the square root. All right, let's work a problem. So let's say we have a problem similar to this. So 40% of people report a quote unquote fear of flying. In a random sample of 1,500 people, 630 reported a fear of flying. So we're talking about our sample now, while this statement right here was talking about everyone, our population. What is the probability that 630 or more out of a sample of 1,500 people will report a fear of flying? First thing we have to do is, can we even use a normal distribution? So we need to check that. So n in our problem was 1,500. P is 0.40. 1,500 times 0.40 is 600. It's bigger than 5. Check that off the list. N times 1 minus P. N times N is 1500, 1 minus P is 0.60. That product gives me 900, bigger than 5. So we check the box for the normal distribution. We can use this key. So let's go ahead and calculate it. Now, this is equivalent to, right here, finding that the probability of the sample proportion is greater than 630 out of 1500, or 0.42. All right, so the mean is 0.40. The standard deviation, standard error, if you put this in your calculator, and I would go ahead and check it just to make sure that you are putting all this. Well, I'll tell you what, I did it. You can see it on my calculator right there, right? So 0.4 times 0.6 divided by 1500. Notice I didn't close that parentheses right there because I want all of this under the square root. And it turns out to be 0.012649. I always go on these standard errors, I always go out to about 6 places. That way you get a more technically accurate answer. All right, so we need what? Greater than? And we need greater than 630 out of 1500. All right, hit compute. So our probability would be 0.0569. All right, gang, that's all I got for you. Next video, we'll dive into some problems on my stat lab and see how we work this stuff. All right, take care.